Okay, we're going to do 3 of the methods out of the binary tree. Before we get there, I'm just going to increase the size here and give you a couple definitions. So we have the depth of a node, the length of the path from root to that node. So let's say if we want the depth of node with label D here, it has depth 1 because we're using one edge up to the root. If we look at the depth of node 8 labeled H, it's got depth of 2. And similarly, if we look at the depth of node labeled K, it's got a depth of 3 up to that's the length of the path up to the root. The height of a node is the length of the path from the node to the deepest leaf. So now we're only thinking about with height, which leaf is furthest from the root. So here in this example with our tree, it's got a height of 3 because the leaf node with label K has the longest path to the root, and it's the deepest node in the tree, rooted at A. So we've got this tree with height 3. So when you're thinking about the height of a tree versus a height of a node, just keep in mind that the height of the tree, you're looking at only the root and thinking about all the leaves, where if we want the height of a subtree, let's say the height of a node E, what's the subtree rooted at E? So the height of the subtree rooted at E would be 2, because K is still the furthest node from this subtree that has a root E. Okay, we want to be able to program to calculate the height for our trees. So when we take a look, I'll just jump down to that code. We're going to take care of implementing these 3 methods. We want to do the size. Size is really easy to describe because we're calculating the number of nodes in this tree rooted at the node that's passed in. So notice that it's static. We're not calculating it for the instance of a binary node for the class. When we create an instance of it, we're going to call it through the class and then pass in a node. We're interested in calculating the size of this node. How many nodes are in its subtree rooted at that node? The height, we already took a look at the definitions for depth and height, so we're going to also write the method for this one and calculate the height for any subtree rooted at a node T. It's also static for the same reason, because both of these we might want to calculate the size or the height for an empty node, because in the trees that we have instanced down at furthest at the bottom of the tree, the leaves, they do not have left or right child nodes. They are empty. So for that reason, we will end up calling the method size or the method height by passing in null in that situation, even though we refer to it in the node as left and right. Sometimes those are null. And so the size of a null node would be 0, and the height of a null node would be 0. This third method, it's got a recursive implementation, and it's only very few lines, a couple lines of code, and we'll take a look at that and implement that one as well. So we'll jump down to figure 18.9 next. Okay, so figure 18.19, we've got the size we're going to calculate for some node, and it has to do so recursively because it's going to count how many nodes are in the subtree rooted at T. If T is null, we're just returning 0, so that's the base case. Otherwise, we're going to count the current node T, and then we're going to add on the number of nodes in the subtree rooted in its left child, together with the number of nodes in the subtree rooted in the right child. So it's pretty straightforward. We can implement that very quickly. Let's do that. Okay, so we've got this here, and you'll notice this one, we've got the type passed in because it's static. We can call it through the class, so potentially we are not working with any other instance from the client code. And so it's not automatically going to know which type we're talking about unless we specify. I'm hoping that it will imply which one so that we don't have to give it as part of the method call based off of the node that we're passing in, because we do have the type right there. Hopefully the compiler can imply which type we mean. So I'm going to take a look at compiling now. We haven't used this method in our application code yet, and we're just compiling binary node.java. So we're fine there. If we were to calculate the size of our tree, I would expect it to do a value of 3. So if we do system out print line, and I'm just going to directly grab it from, do we have a get root method? I think we do, yeah. So normally we would not do this in our client code. We'd have our tree get root and then call size on it. Whoops, it's static. So I'm going to pass that in as a parameter. And we call it through binary tree, or sorry, binary node size. Hopefully it can imply. Let's find out. If there's an error, it likely means we're going to have to specify. I don't need to recompile binary tree. I do app. And when we run, what do we do? So we do correctly get the value of 3 for the 3 nodes that we have in our tree. So just a very small amount of debugging to get started with. We want the wrapper methods for these because in the binary tree data structure for the class itself, it's really just wrapping what the nodes are doing. So when we take a look at code in binary tree, you'll just see the size method. It's just called. Okay, so there we go. Size method in binary tree is just, you can think of it like being a wrapper for the node method call to size. And of course, we want the size of the entire tree. So we're passing in the root node in order to calculate how many all the nodes, how many are there in the entire tree itself. Okay, let's do that really quick. I guess we'll do it right above set children and after get root. And I'm assuming this one needs to be called on the tree. It's not static, so let's go back and take a look real quick. Yeah. So when we call this one, depending on the instance of binary tree we have created in our application, it's going to call according to that instance's root. So we could have different binary trees, and we want to calculate the size dependent on each instance. We're not passing in any nodes either. So it's kind of like a driver as well. They've talked about that in the previous chapter where you just hook into some of the function. It's friendlier for the user to work with driver method call rather than something that would be typically private. So we would want to return, we do binary node dot size. We're passing in the root. That should do it. Let's give it a compile and a run. And then in our app code, instead of doing this call now, we can do tree.size, which is much nicer to look at in our application code. have their same behavior. So I think it's really good to just go through and take those moments to see, as we adjust and implement the code, how things get cleaned up in app. And then as we continue on with the other couple functions and the other couple methods, sorry, I'm going to get rid of this stuff because we should also implement one of the print methods, which are important with trees. We've got different ways that we could traverse the elements of our tree in order to take a look at them. Okay, the next one we would have is height. So that's also implemented in binary node.java. And I'm assuming we've got similar kind of setup. We want to call the height statically because we might be needing to calculate an empty. A node that doesn't have any elements in it, or it's null. We're returning int. We want to pass in some node we're interested in to get the height of it. And then this one, they had it on, let me grab the figure for everybody so you can see. Okay, so this one, a very similar idea, but for a tree that's null, because there is no node, they're returning -1. So forgive me, I think earlier I said a tree that's empty, or a node with nothing in it, you'd have it return 0, but the height of a node, which is a trivial tree, so just a node on its own, there's no path you have to traverse to get to the root, so the length of the path is 0. So in that case, when you have one node, the height would be 0. And they're using -1 as a sentinel for when your node is null. Okay, so otherwise it's similar kind of recursion to the way we were looking at calculating the size. If we have to recurse, then we've got the height of t dot left and the height of t dot right, and it's going to be one more than the maximum of either of those. Now keep in mind that somewhere along the line, both of these will be null, and so that the maximum would be -1, right? And so in that case, with if we only have the one node that's not empty, so it's not null, but it doesn't have a left or right child, then both of these end up being -1. It cancels out with +1. We end up with the correct height of 0 for just a trivial tree with only one node. So let's go ahead and do this one. So if t is null, we would be returning -1. Otherwise, we're returning 1 plus the maximum. And we got to go through the math class for the max method that it has. And it should be short max, right? Yeah. And we want to use recursive call to the height, but we're doing it by passing in the left sub, or the left node child, and then compare that against the height of the right node child. Okay, let's compile that. Back in our app, we would want to test out height now instead. So the height of our tree should be 1, because we only have the root node, and then it has both left and right children. So if we do tree height, once we implement it in binary tree, we would get it. There we go. So compile both binary tree and app.java. And our height is 1. Okay, so we've got those 2 methods implemented. The next one we would want to do is duplicate. So if we've got a tree collection, we have an instance of a binary tree. At times we might want to create another copy of it. So we've also got the duplicate method we'll go through in that one. Again, it's another short one. So we've got 2 more lines than size and height. And it's also recursive as well. Okay, so we've got duplicate. Notice that it's not static. We're returning another instance of binary node, same type. And then the reason why we would want to duplicate and that it's not static is because we don't have to pass anything in. We would be calling this method using some instance that we already have a reference to. And so it's going to use that and have its element. Okay, when we look at our code for binary node, we've got an element stored inside and then null. So it's creating a new root that's local inside this method. So keep in mind that there's no other variable inside binary node called root. So don't get it confused with binary tree like we've got. We don't have any element or any field called root inside binary node. And so we've got the local variable. We're building up another duplicate tree. And we've got left null, right null, but it's going to recurse. And we have to build up all of the children. And it's going to recursively do that. So left duplicate, right duplicate. It's going to keep going down for the entire tree. You can see how all the code in binary node is pretty much doing all the work for what we need for the binary tree itself. The binary tree just ends up being wrapper methods around the node in order to hide the node from the client code. Okay, and then it would return the root because that's of the type, the return type, and that would end up being your duplicated tree. Okay, so let's see. I just go back and forth. We've got duplicate. We're not passing in any parameters. And we want to create a new binary node root. Same type. We know what the element is because it belongs to this current instance, the one that made the call to duplicate. It will have that value of element. And then if the left child is not null, if I remember correctly, let me double check. Yeah. It's not null. We want to recurse. So we'll do root dot left equal to, we would say we could say this dot left, but I think I can just do left dot duplicate. Same deal with right. So we should have a left and a right field to work with. Right here and right here. And we're setting the new trees left and right subtrees. And then we would be returning root. Let's see if I missed anything. I don't think so. There's just the extra comments if you need them. Here's my terminal window. There we go. Java C, binary node, Java. Clear that out. We want to see if we can make a duplicate tree now. We'll do that right away. So we'll do same type. We want it to be the copy, and we'll do tree.duplicate. We don't have the method yet for our binary tree. So we'll come in here and create the wrapper. We are returning a binary tree of the same type. Duplicate. Oh, we could probably get away with the same syntax of curly braces as well to just keep it consistent in style. And we're going to call binary node dot do. Oh no, it's not static. So I can take the root and call duplicate. There we go. So we should be okay there, and then we will print the copy instead of the original tree. And then it says cannot be converted. Oh, did I return the wrong type? I would like to create binary tree though. So I'm gonna have to do new binary tree. That's the part I'm missing. And then this is the constructor where we're passing in. We already have a binary node. So we've got it. Except we can do it for just the root item type, which would be integer type. What are we going to do then? I guess we could create one that's empty and then set root equal to, do we have a set root? We have a get root. We have size and height. We don't have a set root yet. Why don't we double check what we've got in the text? So I'm assuming they're going to have set root method, and we'll create another instance of a binary tree. Okay, so I'm experimenting now where you go to look back at the code for binary tree. They don't implement a duplicate for the tree itself, they're only doing it for nodes. We have it right above, yeah. But it is public, so it just makes me think that we would want to have a similar kind of thing inside the binary tree, and we really wouldn't want to expose any of the internal structure to our client code for working directly with nodes. So it just makes me think in the code, probably the best way to approach it would be I'm creating my new binary tree, I'm just only using the constructor. I mean, we could make another constructor where we pass in a node instead to set the root. But after we create an empty tree, we can just directly set copy.root because we have access to the private variables inside our class. So we know what the structure is internally within the code for the class itself, so we can get away with that even though we're making another one. Set that root to it, return it back. I don't think that should give us any trouble here. It compiled okay. I'm going to compile again for app.java, and then we'll run and we have it printing like we did before for the three values. So for the root and the left and the right child, for that copy, it's got all the same nodes because it's recursively duplicating all those nodes with the same values. We could even check that everything else is working. So do we have the height working as well in our copy? I don't imagine there would be any trouble there because it would behave the exact same way. And the only difference would be we're just working with different memory addresses for different instances of nodes that contain the same values. So really, the functionality of everything shouldn't be different in any way. We're just working with duplicate objects. And that goes not only for all of the nodes internally, but also for the entire tree. It's a duplicate object. It's a completely different, it's taking up completely different memory in RAM. Okay, what else did I want to mention about that? It's called a deep copy rather than a shallow copy, where a shallow copy would just be duplicating a reference to the object of an instance of a tree, but none of the nodes have been copied. So it's actually referring to the exact same nodes. So you could almost think of it as a tree that would have two names. You could use two different variables to point to the same tree, and they would both have the same root object, same root node. So keep in mind there is this concept of shallow copy versus deep copy that we just programmed duplicate to be a deep copy. If we changed the structure of our tree, which we could do after the fact, so our copy, we might insert more nodes into our tree, then that would not affect the original tree because we have made duplicates of the nodes. So if it was a shallow copy and we went to make edits to the nodes, maybe add some more nodes into the tree, then it would also be the same deal back in our alias for the variable name. They would both be pointing to the same edited tree if it was shallow copy. So keep in mind this is the situation when Java's handling memory for you in the background. We still need to pay attention to what's going on with deep versus shallow copies. What does that mean in memory? It's really just duplicates of the objects themselves. So it's taking up more memory with more instances rather than a shallow copy where there's two variables. An alias for the same object in memory. Okay, so if you edit it from one alias, you'll see the edit by accessing it from the other name if it's shallow. Let me stop the video here, and then we'll probably have maybe one more video. We'll finish things up with binary tree for the week.